All right, hi, I'm Noah Weeks, and this is the final demonstration for Group 20's project titled Flowers. You can see here the physical unit that we've built out of plywood that features 3 individual plant chambers. Each have their own plant pot, as well as sensors in each chamber. We have 3, a moisture sensor, a temperature and humidity sensor, and a light sensor. And on this surface here, we actually have LED lights on each shelving face here. So if we come around to the back, we can see how the wiring works. We have a water tank here, and drawing from this tank is this pump here. This is just a 12-volt pump that supplies water to each individual chamber via these PVC lines here. And the way that we actually control the specific amount of water that flows is via these 12-volt solenoid valves. Ultimately, these are actually controlled by a wireless relay here. We actually have 2 identical ones. They're called a Shelly RGBW. And what these allow us to do is to wirelessly toggle on and off these valves here. Additionally, we actually have a main PCB board here. It features an ESP32 chip that will allow us to actually communicate with these Shellys. And we also have on this main board temperature and humidity headers for controlling those sensors. And we also have a set for the light sensors as well. Additionally, on the back here, we see that there's actually 4 unique regulators, 1, 2, 3, and 4. These 3 here each individually power their own moisture sensor, providing the 3 volts needed for them to operate. And we also have this regulator up here, which provides 3 volts for our ESP here. Lastly, on the back here, we have our AC to DC converter. This is providing all the 12-volt power for the shelving. So this includes the pump back here. We also have it routed to each of the 3 valves, as well as to each of the light strips here, connected there. And we also power our Shellys with our AC to DC converter. So this portion of the video is dedicated to showing that our project is specification compliant. On the screen, we'll show our spec table, and we're going to demonstrate that we met a few of these specifications. So we're going to individually show that we've met the soil moisture polling rate spec, that we've met the light sensor polling rate spec. We're also going to show that each environment is individually controllable to show that specification. We're also going to show the valve response time for each chamber to make sure we meet that specification. And lastly, we're also going to show the water pump power consumption specification. All right, so here we're showing the moisture sensor polling rate. We see the values initially while it's submerged in the water, and now we're going to go ahead and take it out and dry it. And we'll see that approximately 1 time every second, the value for sensor 1 is changing. And we see that as we dry it off, the value gets higher and higher to the point where it's now reading within its dry range. So this test now shows the specification for the light sensor polling rate. What we're going to go ahead and do right now is cover the light, and notice the value change in the code happens right away. Within about a second, because that's our polling rate, immediately the lux value drops down from 500 to 3 or 4. And within 2 seconds of him pulling off his finger, we instantly see that the next reading has it back at 500. So let's show that each chamber can be controlled individually regarding the lighting. Let's turn off the middle chamber and turn it back on. Let's turn off the right chamber. Let's turn off the middle chamber. Let's turn on the middle chamber again. Let's turn off the left chamber. Let's turn off the middle chamber. And let's turn on all 3 chambers. Okay, this video is showing the spec for both the valve response time and also the specification that each chamber is individually controlled. So let's first show that the left chamber turns out on. I'll go ahead and turn it on right now. And we see that a slow amount of water begins flowing. We'll go ahead and turn on the right chamber as well, right now. See water begins flowing, still flowing from the left one. Let's turn both of those off right now. And we see that they've both come to a stop. Let's go ahead and turn on the middle one right now. And we see water flowing. Let's go ahead and turn on the left one right now. See the right one isn't flowing. Let's go ahead and turn them all off right now. And they all stop flowing.
Yeah.
Okay, and for this part, we're going to show the specification that the pump is drawing less than 75 watts. So here's me connecting through an ammeter, the pump.
Yeah.
Okay.
A name prompt meets the user when they open the app if a name has not already been set. And at the first open, no plants will be created or assigned to the environment. So we'll start with adding some plants. We will begin our demonstration with the calla lily. In the optional scientific field name, we'll go ahead and fill that out with Santa Decia. That is the scientific name for calla lilies. We will then go ahead and add the photo, which is also an optional field. And we will go through and choose the best options for soil texture, water needs, humidity, lighting, and temperature range. Now, these values will be decided by the user with outside research. However, there will be an About tab within the settings that lets the user have a little bit more information about how our values are calibrated and what those ranges might mean. We'll go very quickly through here as we add the next 3 plants. And again, photo and scientific name are optional, but we'll just add it for all of them for the sake of demonstration. Once we go to the environment, we can double tap each cubby to assign plants to this location on the physical unit. They should be respective to how it looks when you're looking directly at the physical unit. A single tap will bring up the plant's profile, which shows desired values as well as the current sensor readings from the main PCB. Back on the home page, we now have filled in all of the plants in our cubbies, and it is actively pulling the current values and notifying the user of any issues detected in their environment. That is, anytime that a current value does not meet a desired value. Since our design does not affect temperature or humidity, the user can toggle off these flagged as issues in the settings. However, the soil moisture or lighting not matching a desired value will always be flagged as an issue with the cubby environment. The previous app demo shows how it works when there is already a network connected. However, in this scenario, we will look at what happens when there is no stored credentials in the ESP32's persistent data. In this case, we will go ahead and double check that the ESP32 has started itself in access point mode. This only happens if the ESP32 tries the stored credentials and it does not work. So in this case, to make sure that access point mode has started, we will look to see if the F.L.O.W.E.R.S setup network has shown up as given by our instructions. And if not, we can go ahead and enter in our other network field by putting the SSID or the name of the temporary access point, as well as the password, both of which were given in the instruction setup, which we will be returning to in just a moment here after F.L.O.W.E.R.S setup connects. Now, following the instructions, we are going to send on the access point network the ESP32 the credentials of the Wi-Fi we hope to connect it to. In this case, we are using a team member's hotspot. We wait for the credentials, and once they properly are sent and connected, a new ESP32 IP address will be started. In this case, you'll see we connect right back to whatever network we just connected the ESP32 with. This is important. They must be on the same network to be working together. And now when we go back to the home page, we will see that everything is going to be connected and showing if there are any issues in any of the cubbies, as well as the active sensor reading.